I'm trying to make sure to talk to lots of people outside of D-Wave. There's way more smart people outside of D-Wave than there are inside D-Wave. In terms of like, how are they looking to use quantum computing? What kind of challenging problems are they facing? And what tools do they need in order to be able to put, the technology to practical use? And I'm going to try to give you an overview of that, and also some concrete demonstrations of like some of the resources that are accessible to you to get started with, quantum hybrid application development. I'm largely going to focus on like, what can you do with quantum computing? Because I feel, having been out talking with developers, a lot of the feedback I've gotten is if I knew what quantum computers could be used for, I'd be more interested in learning about the technology. So I'm actually going to save some of the material I could talk about in terms of like really ultra low power consumption from the computer processors, or like ultra low temperature operation for the Q&A. And if you're interested in like a little bit more detail about like, well, what kind of technology is involved in quantum computing, I'll go into that at the end, but I'm going to focus largely on some of the practical aspects of putting the technology to use at the start. So I've just got a few slides to start out with, just to kind of give us a bit of a view of like, the space of quantum computing and its breadth, and what kind of resources are available here. And then we're going to shift over to like my browser, and I'm going to actually like show you what kind of resources are accessible to you, what kind of like open source examples, and how to like formulate problems online. And we'll actually run some things in the cloud. So, we've done a lot of market research, and the reason I started with this slide is because this should kind of resonate with everybody here in terms of like a common experience of, as you're working through your development practices, there are sometimes scenarios where you run into a challenge which is very difficult to actually get solved. And in fact, from this market research, there are 31% of companies, like literally almost a third of companies, have abandoned some complex problems because of the time to solve is sort of preventing them from creating solutions. And I spent a lot of time working with organizations, both small and large, in terms of like how to formulate problems for quantum computers to help them kind of get control over that. There are 4/5 of companies that are out in the marketplace are thinking about use cases for quantum computing and their applications in the next 3 years, and 2/5 of them have already started experimenting with quantum computing to date. So, in fact, there's a lot of appetite. There's a lot of interest from like companies large and small. There's universities who are doing startup programs and incubator programs to help get it going. And I think for like developers, it's really neat to sort of think that there's room here to kind of learn the skills that are required to formulate problems for quantum computers and put them to practical use, either for demonstrating like a competitive advantage against other companies and really sort of like setting ourselves apart, or in terms of really just getting more efficient in terms of our operations. Certainly in terms of like trying to have like a higher impact with fewer resources and fewer complexity. Less complexity. So let's bring this to some real world applications. Here is 4 companies who are actually working with our quantum computers today to solve problems, and I'll kind of go through each of them. Menton AI is a company that's working on designing proteins for medical therapeutics. So they're actually taking the task of saying, okay, we've got a particular thing we want to design a protein for. We know how we want it to bind. We need to like assemble it amino acid by amino acid so that it's going to like fold and function the way that we need to. And each time they need to add an amino acid to the protein, they have to be thinking about like a variety of different combinations of amino acids that they could choose from, and how that's going to affect the folding and the function of the protein when it's put into application. They've managed to quantum hybridize that approach, and in so doing, they've actually designed, validated, and chemically synthesized quantum designed proteins, which are now advanced into live virus testing against COVID-19. That's been really exciting to see as we've been working with them over the last 2 years. Save On Foods is a mid-sized grocery company that's based out of Western Canada. Because of the size and scope of their operations, they have a lot of complexity with their grocery operations, and their operations span 3 million square kilometers. So everything from winter conditions any time of the year to desert conditions in certain areas, as well as partnerships, their own brands, their point system. And we've been working with them to actually map some of the logistics and operations challenges to quantum hybrid technologies, and they've actually managed to take a problem that used to take them 25 hours down to 2 minutes in their operations. So that's a great example, particularly because I shop at Save On Foods. Volkswagen has actually been doing a lot of work with quantum computing over the last few years, and they started by looking at mobility and how to sort of improve customers' mobility experiences in terms of being able to do traffic flow optimization to minimize overall congestion. So not just identifying that a particular route is congested and then peeling everybody off onto a secondary route only to have that secondary route get overwhelmed, but actually optimize the whole system to minimize the congestion and maximize the overall flow through the traffic system. They have actually now, from their learnings, adapted that to something that they're using on their production line, which has to do with paint scheduling. So as they're moving cars down the production line, they have to make paint changes, which introduce some waste and some cost in their production process. And they're actually optimizing that to reduce that waste. So they minimize the number of times that they need to do color switches on their production line. And they've been looking at that and developed a quantum hybrid solution for solving that problem. And Denso is a major auto parts manufacturer in Japan. They are looking at tasks associated with factory floor automation, where you have robots and autonomously guided vehicles moving around, moving parts around, and looking at problems where you need to get parts from their locations to the places where they're needed in particular time windows. Now, I'm using these sort of as examples to give you a bit of an idea of like how quantum computing is getting used today. And you'll notice that the applications are actually quite varied. So the reason for that is because a quantum computer, like a classical computer, is actually, it's doing something at its lowest level, at its quantum machine language level, which is very applicable to a broad range of industries. And so it's actually getting used in a variety of different spaces. And I'm partly trying to cover that breadth so that you'll begin to get a bit of a feel for, okay, well, what are the aspects of those problems that are common to them, that kind of link these things together, that make them suitable for quantum computing. And the key aspect to look for is situations where you need to make choices that either happen or they don't happen. They can't be divided down to the nth degree. So, when you're purchasing stock on the open marketplace, in the stock market, you can buy, one stock, two stock, or a billion, right? You can buy a whole bunch of different units. When you're buying a Bitcoin, it can now get divided down to very small levels. But when you are sending a car down a particular route, it's either on that route or it's not, right? If you are delivering a part to material on a factory floor, it either arrives on time for the assembly or it doesn't. So in scenarios where you're trying to do scheduling logistics or applications where things happen, they fail or they don't fail, and those events cascade and create consequences in the rest of the network. Those are areas where classical computers are having a really hard time, and that's the space where quantum hybrid application development is really establishing its foundation. Okay, so why is that happening? What is it about the technology that's kind of that's really getting attention and kind of building? Well, for the past 20 years or so, quantum computing has been largely theoretical. The area of researchers, where they've been developing and testing devices. But just a few years ago now, about 3.5 years ago, some researchers at NASA and Texas A&M actually did a set of benchmarks where they developed tests and a set of competing classical heuristics to compete with quantum computers. And they were able to show that they could find instances where the quantum computers themselves were 100 times faster than more than a dozen other classical heuristics that had been specially designed for those problems. Then about a year later, at D-Wave, we actually published some research in Science and in Nature demonstrating that you can do some very sophisticated quantum simulation experiments with quantum computers that are very challenging to do with classical computers. And in fact, earlier this year, we developed a study where we demonstrated a benchmark of how difficult it is against optimized classical algorithms and software showing that in fact the quantum computer is able to relax to its solutions 3 million times faster than classical computing. That level of speed up, 3 million times speed up, is the kind of thing where at one point in time, perhaps you would have been using, a supercomputer or large clusters to solve that problem. And then at the next point in time, you would only be using quantum computers for it. And businesses are looking at that, and I think technical folks like yourselves, and sort of saying, if that kind of disruption with quantum computing is possible, where in our businesses, where in our missions, and where should we be applying quantum computers for the best advantage? And that's sort of the phase we're looking at right now, which is that creating the products and tools and helping users to quantum hybridize their applications so they can see customer advantage in their applications right now. So Manton, for instance, has actually been finding that they can get to solutions 100 times faster than they could with classical techniques. Save on foods, I mentioned that, taking a problem from 25 hours down to 2 minutes. Volkswagen in that paint shop scheduling, reducing the waste on that production line by 80%. So there are real gains that can be made by using these kinds of hybrids, quantum hybrid solving techniques today. And in the future, at some point, the scientific studies might be done, which sort of say like, hey, these particular problem spaces, you shouldn't be using anything but a quantum computer, but you don't actually have to wait for that later proof point, because actually you're going to find by looking at problem formulations and putting this into application that you can see advantages right away. So what kind of resources are available? Well, at D-Wave, we have the most powerful, most highly connected quantum computer available out in the market. It has 5,000 qubits as quantum bits, which is the fundamental building block of a quantum computer. We've fundamentally redesigned that to make it better suited for business, for practical application problem solving. But what's great, and what you might not know, is that that's actually available in Leap, our quantum cloud service. And that means that right now you can actually log in and get access to this quantum computer and run on it. You can actually load our open source examples right into an integrated developer environment we have in Leap. You can submit problems of up to 1 million variables to some of our hybrid solvers, and they will actually take pieces out of those problems, pass them to the quantum computers, and then pull them back in that problem solving. So there's actually a lot of resources available to you right now. So what is the right way to think about a quantum computer? When you formulate a problem for a quantum computer, what is it doing for you? So think about it in terms of the quantum computer is going to search a vast landscape of possible solutions for you and find the lowest valley or valleys in that landscape and tell you where they're located. Classical computers can also do this. And the way that they do this is they basically run through the landscape extremely quickly, basically looking for downhill runs to find those valleys. And they can, check 5 billion points every second. The one thing to keep in mind is that if you have a problem with, let's say, 300 bits, 300 binary choices, you can actually have a landscape that has more possible solutions than the estimated number of particles in the universe. So just checking 5 billion samples every second is actually a very small undersampling of the solution space. And the possibilities that quantum computing offer is that the ability to actually search the entire landscape and then sort of localize towards some of the best solutions. And that capability is fundamentally different from classical computers, and I think what's most exciting is complementary to it. So the two technologies can both be used to try to accelerate time to solution in problems of this kind. Now, I'm going to talk about a simple example here, and I want to do this in a broader context because the quantum computing industry has really been changing, and the tools have really been changing in the last few years, so that there's kind of 3 layers to the technology stack that you can really think about in terms of what is the right entry point for me in terms of approaching quantum computing. And I'm gonna tell this story from a developer perspective, which is starting at the top of the technology stack and then imagining what it's going to be like to kind of dive deeper down. And it's kind of up to you and to everybody to sort of say, what is the area of the technology stack that suits me best, right? That is kind of the right entry point where I would want to work. So this top one is really about problem formulation. You have some problem in the real world. So let's say we're working with the Chicago Water Works, and we've got a network of pipelines throughout the city, and we're looking to monitor those to make sure that the network is working effectively. So we want to place pipeline monitors at junction points so that we can monitor any of the segments in that network. And we want to do that in a way that minimizes costs. So that task is basically selecting junction points that allow us to cover every segment of the network. And that's called a vertex cover. Now, that if you are looking to program with like our open source tools, this is what a program looks like that allows you to do that. Importing some of the libraries at the start, establishing a connection to the D-Wave sampler here. So this is actually the link to a quantum computer. And then describing the network. So you initiate a graph, which you're going to use to describe the network. And then you basically say, this is what my network looks like. This is where there are edges between junctions in the node, and each of the junctions is labeled with a number. And then you can effectively say, tell me the cover by calling this min vertex cover function, which is going to take that application data, the network that you have. You're telling it, I'm looking for the vertex cover. So it's going to create a problem for the quantum computer and then pass it to it in a way that it can solve the problem. If you're largely looking at, okay, I'd like to figure out the areas of my business or my application spaces where I can quantum hybridize things, you're looking at developing your skills at problem formulation, taking word problems like, I need to optimize, assigning airline crews to flights, or I need to optimize, color switches on a production line, and you're mapping it into a form like this, where you define a network of choices, and then you're asking a system, okay, tell me, how to pick individual options. So that's kind of the problem formulation area. I'll try to make sure that we look at that online as well. There's the next layer down, which is like, okay, once I have that problem formulated, how am I going to make the best use of classical and quantum resources to solve that problem? On Leap, we have hybrid solvers, which allow you to solve these problems in terms of binary choices, in terms of discrete choices where you actually might have multiple options you need to optimize over. But we also have open source frameworks so that you can basically choose, what I'm going to be focusing on is how to combine classical algorithms and quantum algorithms. Not less about the formulation and more about the actual dividing problems up between the resources. And the latter thing is that if you dive into those details much deeper, you can actually look at, okay, there's actually mathematical formulas that are underpinning this formulation. Those mathematical formulas basically give us a set of coefficients so that, this is basically a mathematical formula for minimizing the number of monitoring sites. This is a mathematical formula for making sure that we've got all the segments covered. And there's parameters in here that you can sort of tune and change their weight in order to determine, how do I do this in a way so that the quantum computer can make the best contribution? So that's getting down to the lowest layer to do with the quantum machine instruction. So most of the time when I'm talking with folks in business and developers, they're looking at that top layer of how do I formulate problems for these quantum hybrid products so that I can create solutions to problems. But there are deeper layers in the open source framework to do with hybridizing quantum and classical approaches, and also with understanding how quantum computers are working to create the solutions for these problems. And you can dive in and explore them as deeply as you'd like to go. Okay, so with that, let me just switch over to my other screen, which is this one. Okay, so if you are looking for information about applications that have been built on quantum computers, you can actually just do a search in your favorite search engine, and you'll actually get linked to this site here we have with more information, including different types of applications that have been built, as well as some of the industry-specific examples. If you're looking to get started and actually run some of these demos yourself, all you have to do is just do a search for D-Wave Leap, and any of these links will take you in to allow you to sign up and get access to the quantum computers right now. I've already done that, and I'm logged into the system right here. So this actually shows me how much access I have to the resources, the hybrid resources and the quantum computing resources. Some of the problems that I've been submitting, as well as what is my direct quantum computer usage or my direct my hybrid solver usage on the computers. And this allows us to interact with demos. We can actually get online and look at and explore problem formulation in the context of social networks. So I'm gonna bypass that for right now, but when we get to the the question and answer session, if you'd like to know more about the interactive demos, we'll pop into that. If we go into the resources here, We've got information about that, the ocean software, as well as like the different tools repositories that are comprised, including ones that have been contributed by, Los Alamos National Labs and Recruit Communications in Japan. So external organizations have been contributing to this tool set, as well as some of the programming concepts associated with problem formulation, quantum computing, and the actual hardware itself. And let's pop in here and have a look at some of the ocean code examples. So here we can actually look through some examples. So this one here I like is associated with nurse scheduling. It's about taking a problem of hard constraints and soft constraints and formulating that for quantum computers. I'm going to actually load this directly into our integrated developer environment. This is actually now going to start up some cloud computing resources, create an environment with Thea, and include all the ocean tools so that we can start exploring and trying out this example itself directly. So it's describing the task of how it's building up, hard constraints and soft constraints. The soft constraint in this case is to try to make sure that the nurses all have sort of similar working schedules. This is the Python code. The Ocean software development kit is all written in Python with some components in C and C++ for speed. So this goes through and demonstrates how to construct the problem, and you can actually run it directly in the IDE here. So I'm going to click run. This is now going to submit it to a Leap hybrid sampler, and that means that it's going to provision cloud classical computers and make calls to the quantum computer to reconstruct the solution to the problem of scheduling 3 nurses over 11 days, and then telling us, okay, which nurse is going to be working on which day. So there it is with the answer returned. So this is just with a very simple printed output here over these 11 days and these 3 nurses, sort of showing what their schedules are going to be, making sure that 2 of them aren't working on the same day, that they're not having to work consecutive days, and then trying to make sure that their schedules overall are reasonably equal. Now, the great thing about working with the hybrid solvers is that it makes, it allows you to put your focus into formulating the problem and getting an answer back that you can sort of make use of right away. But we don't want to separate ourselves from the technology itself. So I'm going to go back into the collection of examples, and I'm going to look at one that's to do with clustering, a method for data analysis that a lot of people find useful. And this particular example is actually being constructed with a small data set to actually go directly to a quantum computer and being submitted to the quantum computer. So now I'm booting up a different environment. So again, with a different set of requirements so that they don't conflict. And I can easily kind of look at and explore and operate them without having to do a lot of otherwise like environment setup that takes a little bit more time. And I'm going to go into this example clusters. This is going to generate some data over 9 data points and effectively cluster them. I'm going to start this. And when it runs, it's actually going to submit the problem to the quantum computer, and then it's going to call an inspector, which is actually going to allow us to see the relationship between the problem submitted and what was submitted to the quantum computer directly. And this is largely to make more accessible and make clearer how the quantum computer is involved. So this inspector actually has a little tour. I'm going to skip the tour so I can just get right into the demonstration. I'll zoom out a little bit here so that it's a little bit clearer to see. This is the problem of represented in a graph form. I'm just going to zoom in here, where there are individual variables which then need to be assigned a color in order to cluster them separate from one another. And the relationship of the color choices is demonstrated here through these edges. And here I can look through different solutions. And as I hover through the solutions, you can see that the variable values, the color of the center of the dots is actually changing, demonstrating how the variable value is changing. And there's also room at the bottom here to kind of provide warnings in terms of like how to optimize the parameter tuning for the quantum computer to get the best possible results here. This is a histogram of samples. Each of these dots represents how many solutions did we get of this quality, and going to negative values is basically like going deeper in those valleys to get to higher quality solutions. What's really interesting here is that if I switch view from view 1 to view 2, I can actually see a comparative view between this is the problem that we were working on in the form of a graph of nodes and edges connected to one another, and this is that same graph but mapped into the quantum computer. So these dots now represent individual qubits that are coupled together through these edges. And we can actually go through and say, find a qubit which is qubit 2011, and it'll actually focus us in on that area of the problem. And then it shows us, okay, well, this is the variable in your problem that was mapped to qubit 2011. And what's interesting is that when I select that variable, I can actually see that it got mapped to 1, 2, 3, 4, 5 different qubits. And it did that so that those qubits could create the connections to the other qubits in the processor fabric to be able to represent your problem. So you've literally made a programmable quantum system emulate the problem of clustering the data in the graphs that you're looking at. And that quantum system will actually superimpose itself over solutions and then relocalize to come back with clustering choices, which you can see. I'm just gonna minimize this, which you can see in an image in terms of like the actual data cluster. So let me pause there and make sure that we kind of have time to go to our Q&A.